Here are your 7-6 notes on the natural base, known as E. We talk about the natural base. You'll see LN is the abbreviation for the natural base. So if you see LN, that's the natural base. Okay. So whenever you look at this, we are just doing a little bit to explore with this. We're going to investigate growth of $1. Imagine someone invests $1 at 100% interest for 1 year. Okay. Is it realistic? No. But it's the idea of showing this example. So you invest $1 and you get 100% back in 1 year. Investigate the value of the dollar as the number of compounding periods per year increases. Okay, so you do have to understand what compounding means. So if you have a savings account, your interest might be compounded twice a year. It basically means you put money in your savings account. Let's say you put $100 in, and at the halfway through the year, you get your interest. So if you're getting 2% interest, you get $2. So at the end of the year, you have $102. Then your account sits there, and in the next 6 months, you get another 2% interest on that, and you get interest on $102. So the money in your account is building interest, and then when they put interest on there, you gain a little more. So then you get an account that compounds the interest monthly. That means the end of the first month, you get interest. Then that money plus the interest builds a little more. So compounding is saying how many times they add the interest to your account. The more times you add the interest, the more money you get. Because if you add the money in early, you have a little more money to add to it. So we'll see this here. Find the value rounded to 5 decimal places. In this situation, P is the principal amount. So P stands for the principal amount. We're starting with $1. R is the rate, which is 100%. If our rate was realistic like 2%, we'd put in 0.02. T is the time, and our time is 1 year. So I do need you to understand that. N is the number of times compounded. Number of times compounded. And just so you have this again, P stands for the principal amount. And when we say the principal amount, we're talking about how much money you started with. R stands for the rate, but the rate always has to be given as a decimal, not a percent. And T stands for the time. And you have to pay attention, and this is time in years. So when we do the first one and we compound it annually, that means once a year. So the initial investment is $1. And why is this 1 plus here? Because it's always 100% of your money plus a little bit more. So 1 plus, and our rate is 1, and our compound is 1 time. Oh, that should be a 1 and a 1. So unfortunately, this one starts with a lot of ones, so it doesn't help you to understand the formula. But we start with $1. This is always 1 for 100% plus. The rate is 100%, so 1 and 1 time a year, and it goes to the power of 1 times 1. Now, if you're using your graphing calculator, it understands where the power goes. If you're using another calculator, you'd have to put that in parentheses or simplify it. So I'm just going to say, let's just type it in. I know we could do this one without using a calculator. So if I take the time and type this in, it's going to look like this. 1 parentheses, 1 plus, and then I'm going to go into my fraction key, 1 over 1, close that, and then to the power of 1 times 1. Okay, again, we shouldn't need to use our calculator for this, okay? But the answer is 2. Because if you're getting 100% back, you've doubled your money. You had your $1, and then you got an extra $1. So the value of this account is going to be 2. All right, what does semi-annually mean? It means twice a year, right? So N is going to be 2. So still initial $1, 1 plus the rate, but we're dividing it by 2. And then the semi-annually is twice times 1 year. So the idea is your interest is going to be split up. Now, let's type this in the calculator. My suggestion, so don't retype it, would be to arrow up, select it, and then let's just change out the 2 for the N variable. And I get 9/4. Now, I don't want the fraction, so make it a decimal. You can do that simply by going to math and hitting option 2. Or you just take 9 divided by 4. And we get 2.25. And this is measured in dollars. All right, what does quarterly mean? How many times a year? 4. Okay, so everything's staying the same. Initial amount, 1 plus the rate is 1 over 4 to the power of 4 times 1. So again, I think the quickest way to do this is to select your last thing and then just change over to your n being a 4. And that saves us some typing. And I get 625 over 256. I think I learned something. If you're in here, nope, that's not it. There's another way to get that. But I'm just going to go to math and hit option 2 for my decimal. Tell it, yep, and there it is. Now we want 5 places. So 2.4414, and I'm going to round it up to 1 because it was 0.6. All right, so monthly would be 12 times. Daily would be what? 365. So when I go to do this one for monthly, I'm going to go 1 times 1 plus 1 over 12 to the power of 12 times 1. Now, I can still do what I was doing. Arrow back to take my last thing. And I'm going to replace this with a 12. Now, see how it types over that? I might have to add in. Go down here. And I get 2.613035. Oops, sorry. So what should end up being if I'm going nearest 5 decimals? 4. We're keeping decimals because the numbers are going to start getting close together. Okay, go ahead and do for the 365, and then I will talk about the next couple ones. Do I really need to keep putting the times 1? No, but it's there because if it was, we're talking about something over 2 years or 3 years, we don't want to lose that number. Okay, so I got this 2.7145, 1, 2, 3, 4, and the 6 is going to round up to 7. All right, do you agree with that? So do you see how quickly your number jumped? I know it's not, doesn't seem. It jumped by a quarter, then it jumped by less than 20 cents, and then it jumped by 15 cents, and then it jumped by 10 cents. Do you see how the jump is starting to slow down? Okay. How would you figure out how many hours are in a year? Yeah, you would take 365 times 24 and 8,760. Now, I'm not going to have you fill that in the formula, but if you did this, you're going to end up rounding your answer to 2.72. So I'm going to show you this one more, and then we're going to move on to talk about what's happening. What was the number? 8760. 8760. Do you see how close my number is to the last one? So we did 365 and we got 2.714567, and now we got 2.718. So this only increased by 4 thousandths of a penny. Well, actually not 4,000. Sorry, 4 tenths of a penny, if you will, because we're talking pennies. So the idea is this is about 272. It's rounded up. Every second, well, you'd multiply this by 60, and you get 525,600. And that's going to round to 2.72. And every second, well, every second is 3,001. I don't know where I'm at with the decimals, so let me just do this. Okay. There we are, 31,536,000 seconds in a year. And again, if we type that in, we're going to get really close to 2.72. So use your calculator to find e to the first, and let's compare the number we got. Do you see where your e key is? All right, go down this row and see where it says natural log. That's your ln. See it? So there's your log key and 10 to the x. Here's your ln key, and look at the e above it. So hit second natural log There's e to the first. And look at the number I get. Oops, you can't see it yet. Do you see the number I get and how close it is to the numbers I just had? So this E stands for like a continuous compounding. If it just kept rolling over. Every second's pretty continuous. So the closer we get to every second, every millisecond, the closer we get to this number. So e to the first, I'm going to write it out as far as I know, 2.718281828. Now we round e to the first to be 2.72 for the most part, but you have rounded it. So this is still rounded. This still goes. So that's why it's approximately. E is like pi. It's an irrational number. Is that what you're asking me? E is like pi. It goes on forever. So this is what our calculator shows us. This is what it rounds to. Okay. So E is all about this whole idea of compounding something. Now, that's why we started with $1 and going 100% interest, because it gave us this idea of E. Okay. So natural log is something that is a little bit different, but it truly is a log. All right, as n gets very large, interest is continuously compounded. So we started out with annually once, semi-annually twice, quarterly was 4 times. And if you go back, our numbers were starting to get closer to that 270 something. Do you see? The more times it was compounded, the closer it got. So this is the idea that it's continuously compounded. And it's found by this function, 1 plus 1 over n to the power of n. That's why we started with the $1 out front. This function has a horizontal asymptote, and that horizontal asymptote is at y equals e. The graph's going to get really close to that 2.718, but it's never actually going to reach it. Okay? So e, remember, e is approximately that 2.718 ... It is a number, but we use e just like we use pi to represent 3.14 ... Okay. As n becomes infinitely large, the function approaches this 2.718218. This number is called e. There it is. Like pi, constant e is an irrational number. Okay? So now, this is the graph of your function we were just looking at, where if we have an exponential function, notice it goes up. Guys, remember, these are inverses. Log is the inverse of a base 10, or exponential, and natural log is the inverse of e. All right, exponential functions with e as a base have the same properties as functions you've studied. The graph e to the x is like other graphs of exponential. The difference is, like here we have 3 to the x. Here I have e to the x. Well, e is saying 2.718 to the power of x. So we can treat e like we treat a number. The domain of f of x equals e to the x is all real numbers, because as your graph goes left, it also continues to go up and push right. So all real numbers. But the range is just like the other exponential functions, y such that y is greater than 0, or you could say 0 to infinity. So this is going to have an asymptote right here at y equals 0. Okay, so a lot of just looking before we get to the properties. Don't ignore this part so you can try to understand it. A logarithm with a base of e is called a natural logarithm. So guys, what I need you to understand is right here. Instead of writing log base e, we call it ln. So if you see log base e of x, that's the same as me saying natural log of x. So log base e is shortened to just natural log of x. So whenever you're doing these, you can always rewrite the natural log as a log base e. That might help your brain. So this is just a shortcut. And you know, if you just say log of x, that's log base what? 10. Okay, natural logarithms have the same properties as log base 10 and logarithms with other bases. So all of those properties are going to be used again, but with the natural log. All right, the natural logarithmic function f of x equals natural log of x is the inverse of the natural exponential function e to the x. Okay, if you think about the natural log of x, just think about it. Isn't that the same as me saying log base e of x? Natural log of x is the same as log base e of x. So think about converting this. Your base is e, and we're trying to find x to get that y. Remember, you would find the inverse by flipping x and y and solving for it. but there's your base. All right, the domain is the original range, and the range is the original domain. So here is the graph, exponential form, e to the x, just your typical exponential, and here's your natural log, which is logarithmic form, log base e. Okay, so all the properties that we've learned in all the lessons are still in play. Okay, now, what is the value of the natural log of e? Think about that. Now, one of you, I helped you with a problem. We talked about this. What is the value of the natural log of e? Well, I can tell you it's 1. Can you tell me why? You have all the information. I just said it a couple times today.
Seems right.
Well, what is the natural log of e the same as? Rewrite the natural log as log base what? Log base e of e. And anytime your base, you take the same base of your number, you get 1. Because isn't that e to the 1 equals e? So the natural log of e is 1. So that's why I said sometimes rewriting the ln as log base e might help you to see those properties. Okay, if you were unsure, look at your calculator. There's your natural log key. So type in natural log, and then of e, so second and e, and you always have to put a power there. So if we just want e, we're going to use a power of 1, and there it is. Natural log of e is 1. Okay? All right, so a should be super easy. Why should a be super easy? We can use mental math. We don't even need a calculator on it. Well, natural log of e is the same as log base e of e, isn't it? To the negative 2x. And isn't that product property? This is negative 2x times log base e of e. And what's log base e of e? 1. So it's negative 2x times 1, and my answer is negative 2x. I didn't have to show it that way. This could come out front, and you have negative 2x times natural log of e, and natural log of e is 1. All right, so think about this one. What do you think about option or problem B here? Answers? It's mental math using properties. The answer is x minus 1. I have no work I need to do. Why? Do you remember this rule? B to the log base b of x equals what? 1. Remember, if you have a base raised to the log with the same base of something, not 1, equals x, sorry. So this is e, and if you think about it, it's e to the log base e of x minus 1. Well, base and log base e cancel, and we're left with just x minus 1. So I'm really just using my properties. Okay, now what about C? How are we dealing with C? That one's a little bit different. Thoughts on it? No one? Guesses? You have the answer back there? Yeah, any of you. What do you want it to be? No. When it's multiplication, we could rewrite this as e. It's 5 times, so wouldn't that be the power? E to the natural log of x to the 5th. So let's just break this off. You know how the power is 5 times the natural log of x? Isn't that the rule that would go up top, be the natural log of x to the 5th? So my answer is x to the 5th. Now, if you want to see that, that's the same as e to the log base e of x to the 5th. But it was the idea that 5 had to go back up in its power position. Okay, next. Gotta find it. We have some more examples. So we need to switch between exponential and logarithmic form. Notice this has an e there. So what are we going to use? Instead of log, we're going to use what? Yeah. So if you really wanted to, you could write this as log base e of 6 equals x. I'm using the same rules. Oh, I don't want to write log base e. Sorry, ignore that. Well, okay, it's fine. I did log base e of 6 equals x. Now, you wouldn't write log base e. How would you write that? Natural log of 6 equals x. So anytime you see the natural log of anything, that is the same as saying log base e of it. So if you're comfortable just jumping to natural log of 6 equals x, that's fine. But if not, change it to the log form you're comfortable with and then rewrite this. Okay, so if I'm thinking about that, this would be log base e, that hasn't changed, of 1.97, and it's approximately 0.68. So I think that helps a lot of people rather than just guessing. The base is the base, log solve for power, so 0.68 is my answer, but write it as a natural log of 1.97 is approximately 0.68. So I do think that using your log helps you, and then log base e transfers to natural log. Okay, now, this was exponential form. We wrote as a log. This is logarithmic, write as exponential. So what do you think? Well, if you're unsure, rewrite it. Now, ln stands for log base e of 5 is approximately 1.61. Okay, so I expanded my natural log to be log base e. If that helps you, use it. So that's e to the power of 1.61 is approximately 5. See, e to the 1.61 is 5. If we type that in the calculator, we'd get really close to 5, but not exactly 5. Okay, you change the next one. You don't have to do what I'm doing, but I think it helps some of you. So I'm going to rewrite my natural log as log base e of x equals 4. That means I have e to the power of 4 is x. And again, I could type these two in my calculator and confirm it's 5 and get the answer for x. Now, the minute you type e in the calculator, you have rounded it because you've rounded it there. Okay, now the next couple ask you to simplify. So those were just changing forms. Make sure you pay attention to directions. Are you solving? Are you simplifying? Changing forms. Simplify. So what's A? Should be real quick, guys. It is just 5. You were right. Now, how did we get there? Well, this is e to the log base e of 5. And a base to log base e cancels, gives you 5. This is a property that we learned. Okay, what's B? You can't have that product out front, so you're going to rewrite this as e to the natural log of 5 squared. Not 5 times 2, but 5 squared. That multiplication comes out front. So this is the same as saying e log base e of 5 squared. And 5 squared is what? 25. Guys, do you have to rewrite it as log base e? No, you should know that e natural log cancels out. Okay, I'll give you a second. You do the next two. All right, let's go over these. If you guys said the answer to this one is 4, you are 100% correct. If you want to think about this, it's the natural log of, or log base e of e to the 4th. That power property brings us out, so it's 4 times log base e of e, which is 4 times 1. All right, now, when you do this one, here we brought the power out front. Here, I'm going to bring that power back up so I could do it that way and write it as the natural log of e to the 12th. Why is it to the 12th? Because that'd be the natural log of e to the 6th to the 2nd, and a power to power multiply. And natural log of e to the 12th is just 12. So that's one way to do it. That's log base e of e to the 12th. The 12 comes out front, and we multiply. Or the other thing you could have done is you could have brought the 6 out front. and it'd be 6 times 2 is 12, and natural log of E cancels out. So a couple ways you could have looked at that last one.